Okay, so today's lecture is lecture 24, and this is the second last lecture of our semester. So in our previous lecture, lecture 23, we have discussed some circuits, but most important one was the dynamic circuit. So in this dynamic circuit, we used the clock pull up. So we just occasionally pull up and pre-charge the signal, output signal to 1. After that, only when the pull down network is active, then the output value becomes 0. So that was the dynamic circuit. However, there was an issue of monotonicity of input. So in order to prevent such kind of a problem, we have introduced the domino logics. And yes, so this is a lecture. This is related with chapter 10, and so skipping the introduction, we start from the sequencing the static circuits. So before starting today's talk, we have to review the elements called as latches and flip-flops here. So I think that this this concept has been already covered in your previous course called Digital Design in this college, but I just remind you that this is the important concept. So I just wanted to review its meaning. So here we have something called latch, and here we have its schematic. And here we have D, data, and Q, this is the output. So this is a typical way we write down input and output. And here we have a component called a latch. Okay. Let's wait for a while. Okay, good. Here we have input D and output Q, and here we have a clock. This latch just test its input to the output when clock equal to 1. So when clock equal to 1, latch is transparent. So D flows through to Q like a up-upper. So then what is the meaning of this one? So when this is 1, yes, comes in. Then this is basically just up-upper. So we have number and D, then that is just copied to our Q. But point is, when clock equal to 0, then the latch is no longer transparent, and point is now Q is disconnected from its D value. For example, although it changed from 0, 1, 1, 0, 0, 1, 1, 0, however, if clock equal to 0, then it just keeps its previous value. Yes, so this is the one we wanted to have. The one point is, okay, so when we have clock equal to 0, so then sometimes you may say that, oh, Q is not determined by D. However, point is, it keeps its previous value. So this should be a stable output. So sometimes, for example, if we consider tri-state, then if we have the signal corresponding to 0, then enable signal equal to 0, then actually output is disconnected from its input value. However, at the time, it just become a floating node, so we have no control over its output value. But on the other hand, in the case of a latch, we say that this Q just keep the previous value firmly, so that should be a stable state variable. Okay, so I think that is not that difficult to understand. So let's have a look at this diagram. So when clock equal to 0 in this phase, actually whether we have any value here doesn't make any difference. So Q just takes its original value. Yes, to here. After that, now clock becomes 1. In this case, now the value of D is sampled here and is copied here. Of course, with a certain delay, but anyway, that is copied. After that, here you can see that during the clock is on, then we have a falling edge of data. Then that is just copied into Q. So here we have another rising edge. However, now you say that here clock equal to 0. So in this case, we have no connection between D and Q. So this value, or this value, more exactly, this new value of our D is not copied into our Q value. So simply speaking, when clock equal to 1, it becomes transparent, and when clock equal to 0, then it keeps its previous value, that is the latch. And another one is flip-flop, and it is an edge triggered device. So here we have still D and Q, and data is passed through Q. However, the difference between latches and flip-flop is previously latches just becomes transparent whenever clock equal to 1. However, in this case, in the case of a flip-flop, D is copied to Q only when we have the rising edge from 0 to 1. I think that it's like we can make an analogy like this. So what can I say? There is a lazy guy. He or she always sleep, and of course we have a sun and moon, and this is daytime and this is night. So in the case of latches, it's like this. He or she just wake up and hanging around when sun is in the sky, so in the only daytime, and in night then just at rest and do nothing. This is kind of the action of a latch. However, in the case of a flip-flop, it is related with only when sun starts comes in, only twilight, then either he or she wake up and do something within a short time, like 4 or 5 minutes. After that, he or she just rest. So this is the difference between my own analogy between operation of latches and flip-flops. So it just sends the edge, not the entire clock signal. So now, if you understand this one, then let's have a look at this diagram. So previously, if this is the clock connected to the latch, then actually this time scale will be the active one for our latch operation. However, instead of that, if this is connected to the flip-flop, then only this edge is important. So in this clock signal, where can you find also rising edge? So you can find this rising edge too. Then here you have the opposite one. Yes, here you can see on falling edge. In this case, this is not regarded as valid signal for sensing our D signal, data signal. So only when we have this transition, so from 0 to 1 transition, then the value around this time scale is sensed, and that is affecting the value of our flip-flop output. Okay, for example, if this is a latch, then there will be certain form like this instead of this edge triggering. So since clock becomes 1, so in this time scale it will be sensed, and with a little delay it will be copied. So you know that will be the motion or behavior of our latch output. However, in the case of the flip-flop, we just selectively sense only this time value, and this time value is copied to here. After that, whether we have this transition or that transition, that doesn't make any sense. So here we have just kept value until the next edge comes in. So in this edge, then we can find that its value shown here is 0. So it is now copied to the output with a certain delay. So that will be the behavior of our Q. So similarly, they means that the latch and flip-flop also takes some value of D at a given time to the Q, the output. However, their sensing method or sensing instances are different. So latches, in many cases, it just open, but flip-flop just sense the edge. So it's like a snapshot. So this is the way of sequencing static circuits. So up to now, we have thought about how can we effectively build this combinational logic. So our main focus was laid on, in many cases, delay. So how can we make a fast combinational logic when signal comes in and signal comes out? So we wanted to minimize the, in many cases, minimize the time between the output time and in time. So yes, so if this is short, then we can calculate our logical function quite fast. However, anyhow, they should be synchronized. So here we have a combinational logic, but this is not the only logic we have inside a complicated system. We can have different calculation and different logical operation, and they should be synchronized. Otherwise, there will be certain conflict between this signal and that signal. Say that this one is particularly fast and this one is slow, and eventually we wanted to make certain overall summation of these three components. 1, 2, 3. Then if this is so fast and if they are slow, then eventually the correct operation can be only made these slow signals come, and eventually when we have three stabilized logical signals. However, if we don't make any kind of certain synchronization signal, then intermediately the first COM will generate some intermediate logic value which is not valid at all. So say that we have one signal, two signal, and three signal. They comes in and they are merged. After that, we will use very important logical operation with this 1, 2, 3. But if there is nothing inside it, nothing between these or system, then what will happen? Say that now it comes first, and we have to wait this second and third signal. But before reaching at this second and third signal point, then there will be certain intermediate values, and this intermediate value is fed into our very important logic, combinational logic, and it will generate a certain output which can make a certain decision. This is not a desirable case. Here we must introduce a certain stop. Yes, please wait. All of our signals, input signals, are stabilized and fully valid. After that, wait for a while. Are you ready? Yes, I'm ready. And are you ready? After that, after a long time, okay, second signal is ready and third signal is ready. Then now let's start the logical operation, and that will determine the behavior of a logical system. So, simply speaking, of course, minimizing the delay of our combinational logic is quite important. However, nobody can perfectly match the delay of a certain logic circuit. So even for given logic circuit, you know that depending on the input pattern, for example 1 0 0 1, so let's say that it has 4 inputs, and if we have this input and 1 1 1 1, if we have this input pattern, you know that it generates different propagation delay. So therefore combinational logic's delay, although we have to try to minimize it, however, there is no guarantee that this is precisely become certain nanosecond or certain picosecond. So now, in order to make any kind of logical or reasonable operation, then we must introduce a certain stop point. So regardless whether it comes fast or it comes slow, then there should be certain ones. So now think about this one. Now let's say that traffic. So if we have something like this, then if we have a traffic and here cars comes and cars come and they are merged, and this is the way over their movement. So now let's say that there is many cars. Sorry about my drawing, but anyway, you can recognize it as a car. Then they are going here and they are merging, and if we do not have any kind of a traffic sign, then what will happen? So this signal or this car and that car should see each other and just try to go through in this way. So you know that will be a huge problem for this traffic system. It's like this. So here cars come and cars come, and we have to say that okay, now it's now turn to this right lane, or turn for this left lane. Very similarly, we have to introduce a certain traffic signal for our logic signal. So that is working as this sequential logic. So combinational logic generates a certain signal, and for while, for short time, it just remember its value, and after that send it to the next stage of a combinational logic. That is the way of building a logical system. This slide just shows three different ways to implement static sequential circuit with different memory elements. Different memory elements here, I mean that flip-flop or latches. So in this case, it's like this. So here signal comes, and only when here we have a flip-flop and here we have a signal goes up, then at this time, sorry about that, this is time axis here, this is time axis, and in this time point, so now input signals are just instantaneously sensed. After that will take some time to evaluate this combinational logic gate. After that, after some time later, there will be certain prepared signals or processed signal. One is fast and the others are quite slow. However, here we have flip-flops, and only when the next signal comes to the next flip-flop stages, then these signals are passed through the next one. Okay, so now you understand this situation. So today I'm trying to give you many analogies as possible. So for example, we have similar analogies like this. It's like a progress of your school system. So there are many pupils here, and yes, they are in the first age, so first year, and teachers are trying to teach them some basic mathematics and Korean and whatever. So now the system is like this. So these guys try to learn something and try to learn something and try to learn something, and maybe there can be a smart guy and just ordinary ones. So let's say that someone learns all of necessary lecture materials quite quickly. Then do we open any possibility to advance to the next one? Of course we have in Korean system, but in many cases, even though he or she study everything for the first year, but we just stay here. After that, when the March 1st comes in the next year, then they advanced to their second year. So what happens if we just allow advance in the school system without having such kind of point for starting new semester? Then there will be, oh, it is my first year, and it is my second year, and this is my third year. Or some guys, this is my first year, and this is my second year, and this will be my third year, like this. Then let's say that if we have to, anyhow, for some cases, okay, here I will make the grand evaluation for these pupils' achievement by using some evaluation, then pass and fail. Then what will happen? So if we take this kind of school system, then we must forever, or it will take some difficulty. For example, this guys, it is quite waste of time, and for this guy sometimes it becomes too long, and so we must introduce a certain synchronizing period to evaluate and make a certain decision. So now once again, these actions of memory devices here flip-flop can be make a certain end of our period. After that, send our information the previous stage to the next stage. So this is the one for using flip-flop. However, we can find also other method like using latch. So here we have using the latch. So now the clock is open, then our prepared signal comes in and it is processed in this logic operation. After that, after some time later, we will have a prepared one. Of course, please note that some of our output value will be prepared quite quickly, and some of them will be prepared only at the end of this procedure. So fast one and slow one. So if we don't have any latch here, then that will be just transparent and it will go to the next stage. However, in this case, we introduce another latch, not synchronized by this our clock signal, because if we share the same clock signal, then yes, then if we have this one, then there will be certain action. After that, we have to wait for a while. So now we introduce the another unsynchronized one. So when everything is prepared, then this second clock allow to send it to the next stage and it is processed. After that, we can reuse another one. So that is one way. However, it seems a little bit strange, two-phase. So we can also think about pulsed latches. So it is very similar like the operation of flip-flops. We just quickly sense the output or input of our system. So if we introduce pulse signal to our latches, then although it is how can I say, it is a latch, however the sensing is processed only for a short time. So for a short time, we just send our input signal to the latch output. After that, the clock is now becomes 0, so it is no longer connected to our input signal, and that is processed and we have output signal after some time later. And also this latch or pulse signal, pulsed clock, is used to send it to the next stage. So simply speaking, although the implementations are different, the basic principle is quite easy. I mean that prepare our input data, then just to open the door for a while and sense it. After that, send it to the combinational logic and it will process its output, and this kind of a unit operation is repeatedly done by our combination, our system combining combinational logic and sequential circuit. Okay, so today's main lecture contents will be devoted to then how can we implement these latches and flip-flops using our MOSFETs. That will be discussed this way. Of course, if this course is more focused on the design, then maybe the general design of a certain system will be the main topic. However, as I told you before, this course itself is more related with how can we implement certain building blocks using the CMOSFET. So therefore, we will discuss about how can we build a latch. Actually, flip-flop can be made out of latches, so therefore we will focus on how can we make this latches. So in the textbook, textbook shows many different implementation of our latch and discuss the pros and cons of each design, then eventually give you some acceptable design for the lecture. So we will just follow the lecture progress or contents of textbook. Since the lecture just send D signal to Q only when clock signal equal to 1. Actually, this simple MOSFET can be used as Q or D latch. So think about this one. When it is clock signal 1 and D and Q, if D and Q are different, then what will happen? So for example, let's say that this is 1 and initially this is 0. Then we will have a huge difference between gate signal and source signal. Then there will be certain current conduction, so current will conduct in this way, and now this Q voltage is increasing. So this reaction will be done until what? So instead of this logical value 1 and 0, now I just wanted to say the voltage value VDD and VDD, and if this Q signal is lower than VDD minus of threshold voltage of our MOSFET, then this one gate and this one source has enough power or enough gate overdrive voltage to drive our Q node. However, when this voltage arrive at this voltage, for example, let's say that if we have a threshold voltage of 0.4 volt, and let's say that if our VDD equal to, for example, 1.8 volt, then it means that the voltage of our Q node can be increased only up to 1.4 volt, not 1.8 volt. That is the case. Okay, so are you with me? Of course,
혹시 그 Q가 소스가 맞나요?
yes, in this case, I mean that which one is source and which one is gate. So in the case of our CMOSFET, in the case of our MOSFET, it is determined by which one is lowly biased. For example, so that is a good question with VDD, and if this is biased in this way, then my question is which one is working as source? Yes, this one is working as a source. However, instead of that, if we have 0 and VDD, then my question is which one is working as a source and which one is working as a drain. In this case, this one is certainly working as drain. So please note that CMOSFET has a symmetric structure. It has the same diffusion for source and drain, and actually the role of source is taken by the region having lower applied voltage. So in this case, this is the case.
그러면
Yeah.
제가 이해하고 있는 건 원래 그 뭐지 입력을 소스로 받는 거는 가능한데 드레인으로 받는 거는 불가능하다라고 저는 이해를 하고 있었는데 그럼 이 상황에서는 이 소스랑 드레인이 정해져 있지 않은 상황이니까 어디 쪽으로 입력을
So okay, that is a good question. So when we say that, for example, if we learn something like the microelectron course, we have, for example, this kind of instead of this really. But here we have, for example, certain resistor and resistor, in this case VDD and VG. Then we can think about the configuration of an amplifier. So now we can say that this is a gate, and certainly this is a source, and certainly this is a drain. And we have learned that, for example, we can give certain small signal to our gate. Yes, that can be amplified. Also in this case, we can apply certain small signal to our source. Okay, it can be amplified. However, in the case of a drain, if we insert a certain signal into D, but that is not amplified because following the small signal model of a MOSFET, the amplification or voltage controlled current source is working between the voltage difference between source and gate. Maybe you are confused with this concept. Please note that when we say so, this is related with small signal. Actually, when I say that which one is source and drain, it is determined by the total voltage applied to these two terminals. In this case, always the source voltage is lower than drain voltage. Therefore, the role of source and drain is first fixed by the DC bias condition. But in this digital scene, in this case, actually this one can be VDD and this one can be 0, or on the other hand, or the other way around. So this 0 and VDD can be equally possible. So now you understand their roles, whether source and drain, which one is source and drain, can be exchanged quite easily. So your question is really important because this reveals that actually difference between analog application related with the small signal and digital application corresponding to the large signal between 0 and 1. They have different swings. So yes, so is it enough for your question? Okay, so now, okay, his question was quite good, but let's come back to the case. If we have this condition, then now we understand, well, this cannot be raised up to VDD. It will be stopped at VDD minus VT. On the other hand, if we have 0, then since this is always working as the source and we have always quite large the source to a gate to source voltage, so now we can drive our Q signal down to 0 volt. So now we understand if we have VDD, then output cannot increase up to VDD, but when we have 0, then it can be lowered down to 0 volt. So so although we have 0 and 1, 1 and 0 in our input, but the output will be just a little degraded in this way. So this is shown here. It fails to generate a signal from rail to rail. I mean that the signal does not swing between ground to VDD. It is just swing starting from 0 to VDD minus threshold voltage. Okay, now you understand this second statement. And also another one is another one is if we just set a clock signal equal to 0, then it is good to have a disconnection between D node and Q node. Okay, now the change of D node does not introduce any change in its Q node. It's good, but as I explained in its latch explanation here, actually the Q signal is not simply disconnected from its D value, but we must have Q value is kept as its original value. So when clock becomes 0, we have to have the memory effect. However, in this simple implementation, which one just keeps this Q value? There is no mechanism to keep this Q value. For example, if we have diffusion, of course this is generated as just diffusion region of our transistor, and if we have certain leakage current, then what will happen? Although we have set our clock signal equal to 0, but the Q signal will eventually diminish and approach it to 0. So there is no memory effect actually for our Q value. So simply speaking, the output floats when we apply the 0 clock to our latch. So this is not a desirable behavior. Also another one is, usually we wanted to apply our signal to the gate of our transistor. So please note that if you have inverter, then your A signal is connected to the gate of your transistor and gate of your transistor, and these gates are completely well separated from these channels. They are isolated. This gate and gate are well isolated by this gate insulator. However, in this case, now our our data signal is connected to what? Connected to our diffusion region, actually N plus region. So it generates some problem. Which problem? Actually, if we connect it to this part, that is isolated. And in the case of this signal connected to the source directly, then there is a certain leakage path and another path, so conduction path. So we have no isolation between our signal and current conduction path. So we don't like it. And another one, so we can say here we have state node. So this is quite related with this one, output, this one. This node is just exposed, and if we have other noise comes from other parts, then it can be just disrupted by this noise. So in many ways it is not perfect, but this is really simple, one single transistor, so we have to try to improve it. So one of the problem, like layer to layer problem, So for example, we cannot drive our Q values up to VDD can be easily solved by the using transmission gate. So if we just use the transmission gate, then if we have just a signal equal to 1, then we cannot drive our one value up to one value by using N MOSFET. But fortunately, since we have here now this P MOSFET fully turned on P MOSFET, then now we can drive our Q value up to 1 VDD without any problem. So now we can say that by using a CMOS transmission gate, we can achieve this rail-to-rail output swing. It's good. Mm, it's good, but although it is good in terms of this rail-to-rail output swing, but every other thing is just kept as before. For example, so is the connected to the gate of transistors? No, still it is connected to the N plus region of our N MOSFET and P plus region of our P MOSFET. So this is not connected to the gate. Also Q, is it protected or not? No, it is still just open to the external world. So if we introduce a certain noise into it, then it can be just affected. So simply speaking, so by introducing this CMOS transmission gate, then okay, we can solve this problem. Good. However, still these problems are not solved in this transmission gate. Then now you understand. Okay, then by introducing the inverters in front of here or there, we can solve individual problem of our each point. For example, previously Q was just exposed. We wanted to keep this Q. Yes, and other one Q was just exposed. However, for example, if we introduce an inverter into this one, then our state variable now becomes just X, and it is inverted to Q bar. So now let's say that there comes a certain output noise to Q bar. Okay, now Q bar is slightly modified. Then my question is X affected or not? Fortunately, since this is just an inverter, although Q bar is just perturbed, but still X can be protected because it is hidden and it is not exposed to the external world. So X can be kept safely. Another one is here we have inverter located in front of our transmission gate. Then what is the beauty of this one? Now D, and it is inverted. Of course, the signal becomes D bar, and this D bar signal is applied to this transmission gate. So take from the viewpoint of this D is just applied to a gate of our transistors. So in order to build this inverter, we have P MOSFET and N MOSFET, and their gate is connected to this way. So now D can be quite safe from this diffusion input problem. So it sounds good, but here we have a little annoying thing like this. The overall output of this implementation will be just 2 Q bar. not exactly Q. So please note that the latch just to become transparent. However, now in this implementation, it is no longer just transparent. It is inverted. D is just copied and inverted in these implementations, and you know that each of them solve only one problem. And for example, in this top one, okay, our state variable is protected, but now still it should drive the open one. So I mean the diffusion input. And this one case, okay, now we can avoid the diffusion input problem, but still this output value or our state variable is not protected. Then obviously maybe you can have just something like we can add both of inverters in front to it and after the transmission gate. Okay, we will see later. But most important thing we have to keep in mind is even in that case there is no guarantee that the keeping the output. So in many cases, in every cases studied up to now, we just say that when yes, so when clock is low, then yes, there is no way to, how can I say, make it strong and kept as strong. Of course, I wanted to say that, so think about this one. Even in the case of this transmission gate, if we apply zero clock, so then now it becomes just a vacuum. Then if we apply 0 and 1, even our N MOSFET and P MOSFET are just turned off and Q is just floating. This problem is never solved by introduction of a transmission gate. So we need some capability to keep the state variable safely. Please note that this is a little bit different from just a little bit different from the issue of exposed. So that here they seems to be quite similar and related, but they are a little bit different. So this one and that one. Okay. Then let's have a look at this one. If we introduce this kind of implementation, then something is changed. Let's have a look at it. When clock equal to 1, okay, then it becomes transparent. So now it is just copied into this way. Then please note that here we have a feedback tri-state, and it is enabled by actually clock bar, not exactly clock. So when clock equal to 1, then clock bar is entered into this one. So now this feedback tri-state says that, okay, this one, its enable signal becomes 0. When enable signal becomes 0, what happens to this guy? When we have enable signal equal to 0, then state of this tri-state output becomes just float. Oh, sorry about that. This x is not related with this one, so it becomes just float. So we have an undetermined one, but fortunately in this case D and X are strongly coupled, so we can say that, okay, when clock equal to 1 and X becomes just a copied version of our D. Good. Yes, however, it was also good even without this feedback tri-state, the real strength comes from when we have clock equal to 0. Without this one, actually there is no mechanism to keep it. However, when clock equal to 0, of course this transmission gate does not play any role. However, now we have this feedback tri-state enabled. Now it is enabled, so you can see that between X and Q bar we have just two coupled, no, two coupled inverter chain. So now X becomes X bar and X bar becomes X. So now using these two serially connected inverters circulating, now we can keep this X value in a stable way. Okay, good. So the feedback tri-state turns on and holding our state variable X at the correct level. So now using this feedback tri-state, now we can make the stable output. Even though we have certain leakage current, but still we can have the stable X value. Then the remaining things are quite easy to understand. Okay, okay, we have solved a big problem, but still here we have input directly connected to the diffusion. So now say that we can introduce another inverter. The only difference is here. So now we can separate our D signal directly connected to our diffusion node. Yes, and also when we introduce this one, since now we have D bar actually as a internal system, so now D bar is copied to X, and here we have another inverter, so the output Q becomes just D O. So please note that in this one, although we have a holding property, but the output is not exactly the D, but we have D bar is used as Q. So this is solved by adding this additional inverter. Finally, please have a look at the last line. Okay, good. But if we use this Q as output, actually we have here feedback loop. Yes, and if we use it directly, use this intermediate value as output value Q, then if we introduce a certain noise signal into it, then this noise will just disturb X value. Oh, the reason why we have introduced this feedback value is to make our signal strong. But if we have noise in it, then it will actually destroy our correct value. That is not a good sign. So in the next slide, we just avoid use this intermediate value connected to the other one. So please do not connect this Q. So we do not use it. Instead of that, we will use a separate root to be used as Q. So are you with me? So that's the reason why in our okay. So okay. So here. Oh, I think that I'm missing someone, so sorry about that. Here we have another figure, like a figure 10 to the, maybe if I remember correctly, we have something like Z. But point is, without using this signal as an output, because if we use it as an output signal, then output noise can be entered into our X node. So we wanted to avoid it, but separately, just to make a special route to be used the output. And in this case, we have only unidirectional flow of a signal. The output signal in Q signal cannot make any disturbance on our X signal. So sorry about my missing the slide, but I think that this is all for our okay, so it is strange. So I really missed one slide. So the last one, but the last one just looks like this. Okay. So that is the recommended one. So this is provided in terms of cell library in many cases. Okay, so up to now we have discussed about latches, and in this last slide of our today's talk, we will talk about flip-flops. So flip-flops, then latch just to sense the entire time scale for having the positive or VDD clock. However, flip-flop should not react this entire signal here, but only a short time period. How can we actually sense this one? This sensing can be done by this way. So please have a look at this upper one. I think that just explained everything. Here we have D, and how can we send it to the Q? So here we have two serially connected transmission gate basically. So however, the point is, although they looks quite similar, please note that here bubble is located here and bubble is located here. So this one, the first one, is react when clock signal phi equal to 0, and this signal, the second transmission gate, is open when we have the clock signal equal to 1. This is the case. So you know that. Now think about this one. We have one signal, so clock signal. Let's say that this is a clock signal, and we can have also another signal called clock bar. CLK bar, or in this notation, this one is just phi bar, and this is just phi. So now this first transmission gate just sense when clock equal to 0, it means that clock bar equal to 1. So when we have this diagram, then where do we have clock bar equal to high? So you can understand there will be the time scale here. The clock bar is entirely 1. And of course, here we have certain short range, although it is not perfectly 1, but here we have some small values. Okay, and here we have also clock, which is here we have one value. So now it says that if we have this signal and that is transferred to our transmission gate, so transmission gate having the one, so by using this clock bar, first this D is copied into this output of first one. However, in this period, you know, in this case we have the second transmission gate, and second transmission gate do not allow send it to our eventual Q value. So it is protected. However, only when we have very short time period here. Now, previously, in this time scale, although this first transmission gate is transparent and D is here, but it was blocked. However, here we have a very short time. Like first, this value is copied and now our transmission gate becomes non-transparent. After that, now this second stage becomes transparent, and now this D signal is copied to Q. So only so after this period is over, then let's think about this time period. Then always this second one becomes transparent. However, the value for the second transmission gate is just obtained from the last stage of proper working of the first stage. Therefore, we just sense the value at this point, not this point. Although the second transmission gate is always active in this time period, but the first one just sensed the last time instance of its working lifetime. So that's the reason why we have the edge sensing and edge trigger. Okay. So then I just explained the way having two serially connected transmission lines, but here we have some inverters. Okay, these inverters are introduced to, of course, to have some good properties. For example, avoiding the input directly connected to the diffusion one, or something like so we wanted to also keep the state variable from the output. Also, you can easily understand this one is the basic model, and this one has some additional features having feedback loop, and also providing some other paths. So now, yes. For example, let's have a look at this final one. Here we have a Q bar and Q, and it is always taken by the final inverter operation. So although output noise comes into this Q node or Q bar node, but it does not distract the value of this node or that node. The nodes inside the feedback loop is safely kept and isolated from output noise by introducing these output inverters. So wow, good. So although we have many other topics in this sequential circuit chapter, sorry about that. In this chapter 10, we have a very long discussion, but unfortunately, I will just wrap up today's lecture content, the sequential circuit design, within a short time. It is mainly because our course is devoted to the, how can I say, device point of view for our building blocks. So if you are more interested to the design itself, then please, you will have another courses open by other professors. So please try to attend to enroll those courses. And this is the final announcement. Now we have only one remaining lecture, lecture 25, and that will be devoted to the SRAM. So SRAM is actually quite important in this digital system. Well, in which aspect it is important? So actually, SRAM is SRAM. However, it takes a lot of actual size of your area of your chip. So that is quite important to have efficient SRAM design. So we will talk about that important topic in the last lecture. And please note that we will make the final exam on the next Friday, if I remember correctly. So please come to this lecture room on time, 9 o'clock, and you will have once again 90 minutes long final examination. Okay, so do you have any question on today's lecture contents? So if not, okay, thank you for your attention, and I want to wrap up today's lecture. Bye.